Today we'll be covering section 12.4 on the addition and complement rules. Before we begin, I want to say that most of the problems in this section can be solved using techniques we already know. But occasionally we'll come across certain problems when we need to learn a little bit more about probability, and occasionally we'll find out that it's convenient to use some more formulas and have them in our toolbox. So I'm going to do something that I don't usually do. I'm going to go ahead and give you a listing of the formulas that we're going to add to our toolbox in advance of when we've actually talked about them. I think it'd be good to let you look at what we're going to be using, mainly for the reason that I said earlier, we don't always even need them, but they will be here when we do need them. The first is called the addition or union rule for probabilities. It simply says that the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. And remember, or means union and means intersection. The complement rule. If E is an event and E with a superscript C is the complement of the event, then the probability of E complement is equal to 1 minus the probability of E. The product rule for independent and dependent events. If two events E and F are independent, then the probability of E and F is simply the probability of E times the probability of F. Now the dependent version of this rule uses some notation we haven't even introduced yet, but I'm going to go ahead and do it anyway. We'll come back to it later and talk more about what the new notation means. But it says, if two events E and F are dependent, then the probability of E and F is equal to the probability of E times the probability of F given E, which is also equal to the probability of F times the probability of E given F. Remember, I haven't even introduced that notation where the vertical line is used here in this context yet, but I will. That leads to something called conditional probability, and I've got two formulas related to that. One says the probability of E given F is equal to the probability of E and F divided by the probability of F. Remember, when I say E and F, and means intersection. Also, the probability of F given E is the probability of E and F divided by the probability of E. Before I leave this, I told you I'm going to rotate back to this later, but I will say, if you use that notation with the vertical line, it's read the probability of E given F. The vertical line is read as given, or given that. So of course the probability of F given E when the E and the F are flipped around the vertical line. Like I said, we'll come back to this later, but this is the addition to our toolbox of formulas. Sometimes we'll need them, sometimes we'll just be able to go back and do these problems using the things we already had, but they're there if you need them. Suppose we want to calculate the probability of rolling two dice and getting a sum of either 5 or 9. And you notice I call this getting a sum of 5 an event called E sub 1, and the sum of getting a 9 an event called E sub 2. That's just for convenience. We're trying to roll two dice and find the probability of getting a sum of either 5 or 9. You really don't need any of the new formulas to do this. This is just like a problem we might have been able to work earlier, and I want to emphasize that what you really need to do is build your 2x2 table for rolling two dice, which gives you the sample space, and then look, we're looking for a sum of 5. That's the event I called E sub 1. There are 4 possibilities. You roll 4, 1, 3, 2, 2, 3, or 1, 4, or a sum of 9. That's the event I called E sub 2. There happen to be exactly 4 possibilities for that as well, either a 6, 3, a 5, 4, a 4, 5, or a 3, 6. So the probability the sum is either 5 or 9 is simply how many ways you can get a 5 or a 9, which happens to be 8, over the number of ways you could get any sum, which as we know from earlier problems is 36. WebAssign will accept 836 as the answer, or you can reduce it to 2 9s. But there is something about those last two examples worth noting. There's a difference. Look at those two. I'm flashing on the left, the first one I did, on the right, the second one I did. Going back to the one on the left, the probability the sum was 5 or 7 turned out just to be the sum of the probability that the sum was 5 and the probability that the sum was 7. In other words, there were 4 events that gave me a sum of 5. So the probability of getting a sum of 5 is 436, but there are also 4 that gave me a sum of 8. So the probability of getting a sum of 8 is also 436, and 436 plus 436 is 836. But if you look on the right side, the probability that a number is greater than 2 or odd turned out to not be equal to the probability that the sum was 2 plus the probability that the sum was odd. If you look at it, the probability that the sum was 2, 3, 4, 5, 6, 7, 8, 9, 10 was 8 out of 10. The probability that the sum was odd was 5 out of 10. Well, obviously, 8 tenths plus 5 tenths is 13 tenths, not 9 tenths. So on the left, I was just able to take the two events separately and add up the probabilities and get the correct answer. On the right, if I tried that trick, it wouldn't work. Why is that? It's an important distinction. Think about it just a minute. In a nutshell, it's because on the right, some of the values are greater than 2 and odd. Remember that when we did this problem on the right, there were certain numbers that were both greater than 2 and odd. For example, 3 is greater than 2 and odd, 5 is greater than 2 and odd, 7 is greater than 2 and odd, and 9 is greater than 2 and odd. So there's an overlap between those counts. On the left, that didn't happen. When you looked at the numbers that summed to 5 and the numbers that summed to 7, there was no overlap. That's what caused the difference. Noting this leads to an important result called the addition or union rule for probabilities. Remember, that's one of the ones that I flashed up earlier. It says that the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. And if you look at that formula, it encapsulates the difference that we just noticed between those two earlier examples. You could have used this rule to solve both of the earlier problems, but you don't have to. We were able to figure out a way to do it without using the formula. But I will say that if you did use the formula for the first one, where the events were mutually exclusive, the sum being 5, there was no overlap with the sum being 7, there was nothing to subtract away. If you take that minus part of the formula, it would have been 0. The probability would be 0 that a sum could be 5 and 7. However, on the second one, there was an overlap. There were numbers bigger than 2 that were also odd. This formula takes care of that. Think about that, what that means. If the events are mutually exclusive, the probability of them both occurring together is 0, so you're actually subtracting nothing. So the formula also allows for the possibility that overlap is not probability 0. So the formula works either way, but if they're mutually exclusive, remember there's just nothing to subtract. The formula just degenerates to having to subtract nothing. Now let's look at some problems where we might want to think about it in terms of using this formula. If we select a single card from a standard 52 card deck, what is the probability that we draw either a heart or a face card? So the probability of a heart or a face card. Recall what this standard 52 card deck looks like. It has 4 suits, 12 face cards, etc., etc. So the probability of a heart or a face card is just going to be the number of hearts or face cards over the number of cards in the deck. Well, if you look at the hearts or face cards and just count them, the face cards are the cards that actually have faces on them, and you've got the hearts as the other possibility. If you just count, you'll see that there are 22 of them over the number of cards in the deck, which is 52. So you get 22 over 52, and if you want to reduce it, you get 11 over 26. Suppose I wanted to actually use that addition rule rather than just figure it out as I just did here. It would still work. I would just simply take the probability of getting a heart. Well, remember, there are 13 hearts in the deck. So the probability of getting a heart is 13 over 52. Then I would calculate the probability of getting a face card. Well, there are 12 face cards in the deck, 4 jacks, 4 queens, 4 kings. So the probability of getting a face card is 12 over 52. And if I apply the formula, I'll see that I still need to calculate the probability that a card is both a heart and a face card. And if you look at the picture, there are 3 hearts that are also face cards. That's the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So the probability that the card is both is 3/52. And if you plug into the addition rule formula, you'll notice that you get the probability of getting a heart is 13/52, plus the probability of getting a face card is 12/52, minus the probability that you get a card that's a face card and a heart. That's 3/52, and that's 13 plus 12 minus 3 is 22. So you get 22 over 52, which is 11/26, which is exactly the answer we got earlier by doing it without using the addition rule. So this is just another example of where the addition rule works, but you could really do it without it. Here's an example where using the rule is really the best way to do it, the most straightforward way to do it. It says if the probability of A is 0.3, the probability of B is 0.4, and the probability of A and B is 0.2, find the probability of A or B. Remember, and is intersection, or is union. So I would say the most straightforward way to do this particular problem is to use the formula. If you write the formula down replacing E and F with A and B, you get the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Well, we know the probability of A is 0.3, we know the probability of B is 0.4, and we also know that the probability of A and B is 0.2. So a little bit of arithmetic tells you that the final answer, the probability of A or B, is 0.5. That's the most straightforward way to do it. Another example where the formula is the most straightforward way to do it. What if the probability of A is 0.3, the probability of B is 0.4, the probability of A or B is 0.5, but this time we're looking for the probability of A and B. So it's the same formula, but you know different things. Here you know the probability of A or B is 0.5, the probability of A is 0.3, the probability of B is 0.4, and you're looking for the probability of A and B. It becomes a small algebra problem, but it's easy enough. 0.3 plus 0.4 is 0.7. If you move the negative probability to the left and move the 0.5 to the other side, making it negative, you'll end up finding that the probability of A and B is 0.7 minus 0.5, which is 0.2. These are both examples where using the addition or union rule for probabilities is the most straightforward way to solve the problem. Use the following table to find the probability that a randomly chosen member of the Student Government Board is a freshman or lives in off-campus housing. They give you a table. This is another problem where you probably can just do it by the old techniques. You want to know the probability that a person is a freshman or lives off campus. So you look at your chart. There are 5 freshmen and there are 5 students who live off campus. So we want to know the probability of being a freshman or living off campus. You can't just say 5 plus 5 because there's one person who overlaps. There's one person who is a freshman but also lives off campus. So when you count the number of freshmen or students living off campus, you have to say 4 plus 1 plus 4. That's only 9. And then when you count everybody, you get 4 plus 1 plus 2 plus 0 plus 4 plus 2 plus 1 plus 0 plus 4 plus 0, 0, you get 17. So the answer is 9/17. Again, you could use the addition rule to get the answer, but I would recommend just doing it straightforwardly. Consider the experiment of rolling 2 dice. Let A be the event of rolling a sum of 8, and let B be the event of rolling a double. A double means you get the same number on both dice, like a 2 and a 2 or 5 and a 5. Find the probability of getting either a sum of 8 or a double. Again, when you're rolling 2 dice, you think of that as a 2-stage experiment, so you build a table. We've talked about that before. The probability of getting an 8 sum or a double is going to be the number of ways of getting a sum of 8 or a double divided by the number of ways to get any sum. So if you look at the numerator, let's first look at the number of ways of getting a sum of 8. You could get a 6-2, a 5-3, a 4-4, a 3-5, or a 2-6. Then look at the number of ways to get a double. You could get a 1-1, a 2-2, a 3-3, a 4-4, a 5-5, or a 6-6. If you want to count all those possibilities, notice there's an overlap of 4-4. So when you're counting, you don't want to count that 4-4 twice. If you count them, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't count that 4-4 twice. So that gives you 10 over the number of ways to get any sum. Well, as we've learned from doing these type problems multiple times, there are 36 possibilities. So the answer is 10 over 36, and if you want to reduce it, you get 5/18. Again, we didn't have to explicitly use the addition rule for probabilities, although you could. Let's go to the complement rule that we introduced in our toolbox at the beginning. The complement of an event. Let's take an experiment where we're rolling a single ordinary dice. The sample space obviously is going to be either 1, 2, 3, 4, 5, or 6. So if we want to look for the event that we rolled a 3, the probability of doing that is the number of ways you can get a 3, which if you're rolling a single die, there's only one way to do that, over the number of elements in the sample space. So the probability of rolling a 3 is 1/6. The complement of that event, and we're going to use the notation E with the superscript C. Some texts use E with an accent symbol like we used back when we talked about regular set operations, but if you see it either way, it means the same thing. E with a superscript of C or E with an accent symbol. It's sort of, in a sense, the opposite of the event. So if you're looking for an outcome, the complement is everything except that outcome. So if we're talking about the problem we did above, if the event E was getting a 3, then E complement is not getting a 3. So in this case, if we wanted to write out E complement, it would be everything except 3. So it would be 1, 2, 4, 5, or 6. So when we're talking about the complement of event, that's what we mean. Everything but what makes up the event. There are 5 things that aren't 3s out of possible 6, so you get 5, 6. And notice that the probability of getting a 3 is 1/6, and the probability of not getting a 3 is 5/6. And that's not a coincidence. That's what the complement rule says. It simply says if you know the probability of an event and you want to know the probability of the complement of the event, you just say 1 minus the probability of E. And the importance of that rule is, it seems sort of obvious, but it's very useful because some problems it's really easy to calculate the probability of an event, and it's a little more difficult, or more than a little more difficult sometimes, to calculate directly the probability of the complement. But if you can calculate the probability of the event, all you have to do is say 1 minus that probability, and you'll automatically have the probability of the complement of the event. So this is important. It's a very handy tool to have in your toolbox. For example, if I ask you to find the probability of not rolling a sum of 11 when you're rolling 2 dice, again, you'd build your table. The probability of not rolling an 11 is the same thing as 1 minus the probability of rolling an 11. The probability of the complement of something is 1 minus the probability of that something. So it's very easy to calculate the probability the sum is 11 because there are only 2 possibilities. You can get 6, 5 or 5, 6. So the probability of getting a sum of 11 is simply 2 out of 36. So the probability of not getting a sum of 11 is 1 minus 2 out of 36, which would be 34 out of 36. Complement rule is a very powerful tool in your toolbox. If you want to reduce that to 17/18, you're free to. I want to talk about a little bit about the English language as relates to this. It turns out that when we're doing probabilities, we tend to come to these problems where we're asked to find the probability of at least one something. And I want to talk a little bit about that in particular so that when you see it, it won't be confusing. For example, if I roll a standard die 3 times, What's the probability we get at least 1 4? You see that at least 1 quite often. At least 1 4. Well, think about it. At least 1 4 means you get exactly 1 4, or exactly 2 4s, or exactly 3 4s. That's what it means to have rolled at least 1 4 in the context of rolling the die 3 times. One way to answer this question is just to do 3 separate probability calculations and just add up the results. Just find out the probability of getting exactly 1 4, then find the probability of getting exactly 2 4s, then find the probability of getting exactly 3 4s, and just add them all up. That's one way to do it. You could take this, and this, and this, and just add up the 3 separate probabilities. That's quite a bit of work. There's a better way. The better way is to use the complement rule. Because if we roll the die 3 times, there are only 4 possibilities altogether. We've talked about 3 of them. We've talked about getting 1 4, or 2 4s, or 3 4s. There's only one other way, and that's to get no 4s at all. So wouldn't it be much easier to calculate the probability of not getting any 4s and then say 1 minus that? And that's what I'm going to do. The complement rule says the probability of getting at least 1 4 is 1 minus the probability of getting no 4s, because getting no 4s is the complementary event of getting at least 1 4. And getting no 4s is a much easier probability calculation. So how do we calculate the probability of getting no 4s? And this comes back to the stuff we talked about earlier. Remember when we started studying this, I asked you if you know how to count. The solution of that problem requires us to count using some of our combinatoric formulas, and that's why we studied them, so we could use them. So if a standard die is rolled 3 times, what is the probability we get at least 1 4? Well, we just talked about that the easiest way to do it is to calculate the probability of getting at least 1 4 as 1 minus the probability we don't get any 4s. That probability of getting no 4s is the key calculation in the whole problem once you understand what you're trying to do. So how do you calculate the probability you don't get any 4s? Well, I would think of it this way. The probability of getting no 4s is the number of ways to get anything but a 4 divided by the number of ways to get anything with your 3 rows. I think I'll start with the denominator first. Let's find the number of ways to get any 3 rows. Going all the way back to the counting principle, if you're looking for the number of ways to get any 3 rows, remember each row can be a 1, 2, 3, 4, 5, or 6. So think of this as a 3-stage experiment. You can look at how many ways you can get something for row 1, row 2, row 3. The counting principle says to multiply them together. So the number of possibilities for the first row, well, there are 6 possibilities. As for the second, there are still 6 possibilities, and for the third, there are still 6 possibilities. So the counting principle says the possible die rolls you can get when you roll 3 times is simply 6 times 6 times 6, which happens to be 216. That's the denominator. But what about the number of ways to get anything but a 4? Well, after having done the calculation we just did, I think you'll see that it's pretty easy to look at the numerator and see that it's the same thought process, but this time we're not allowing the possibility of getting a 4 because we're looking for the number of ways to get anything but a 4. So we knock the 4 out as being a possibility, but the process stays the same. We're still doing 3 die rolls. We just don't want any 4s. So there's only 5 possibilities for the first die roll if you don't want it to be a 4. There are only 5 possibilities for the die roll 2 if you don't want it to be a 4, and there are only 5 possibilities for die roll 3 if you don't want it to be a 4. 5 times 5 times 5 is 125, so the probability of getting no 4s is simply 125 over 216. But that wasn't the final answer. We want to know the probability to get at least 1 4. The key calculation was getting the probability of no 4s, but it wasn't the final answer. The probability is 1 minus that, which would be 91 over 216. How about this? If you draw 3 cards from a standard deck without replacement, what is the probability that at least one is a face card? Write your answer as a percent rounded to 1 decimal place. So as we learned, the probability of at least one something is 1 minus the probability of none of that thing. So in particular, the probability of at least one face card is 1 minus the probability of no face cards, or 0 face cards. And as we've seen before, that probability of 0 face cards is the key calculation. Well, what is the probability of no face cards? There are 12 face cards in the deck. We've done this multiple times, so that means there are 40 cards that aren't face cards because 52 minus 12 is 40. So we think of partitioning the deck into face cards and non-face cards. There are 12 face cards, there are 40 non-face cards. So the probability you don't get a face card is the number of ways not to get a face card. In other words, the number of ways to get anything but a face card divided by the number of ways to get any 3 cards. We've done these problems in earlier sections. When we're drawing face cards, we don't care about order, because when you pull a card out of the deck and put it in your hand, it doesn't matter what order the card came into your hand. So this is a combination. If we're trying not to get a face card, we've got to draw from the 40 things that aren't face cards. So it's a combination of 40 things, and we're choosing 3 cards, so it's a combination of 40 things taken 3 at a time. Down bottom, when we don't care what the cards are, it can be any of the 52, but we're still drawing 3 cards. So it's a combination of 40 things taken 3 at a time, that's the number of ways to get anything but a face card, over a combination of 52 things taken 3 at a time. That's when you don't care what the cards are. You're drawing 3, but you don't care what they are. And in case you really have forgotten your shift combinations to get your calculator answer, I put them there for you. I hope you didn't need it. They ask you to do a decimal approximation, so you need to change that now to a decimal. That's 0.44706. They ask you to change it to a percent rounded to 1 decimal place. So take plenty of decimals because you have to change it to a percent and then round it. So do not just write 0.44, write several decimal places. So it's 0.44706 to several decimal places. So you continue your calculation. The probability of getting at least 1 face card is 1 minus the probability of no face cards, which we've calculated to be 0.44706. Notice I'm emphasizing yet again, carry plenty of decimal places during this calculation. Round off in the very last step. To do that subtraction, you get 0.55294. You're still not ready to round because it says to give your answer as a percent rounded to 1 decimal place. So you first change it to percent and then you round. You sort of see now why I'm emphasizing how important it is to carry plenty of decimal places. Now change it to percent, which means you move the decimal place 2 places to the right, and finally you round that to 1 decimal place. Suppose we take the problem that we just solved and change it ever so slightly so that now we're drawing 3 cards from a standard deck, but we're drawing with replacement. We still want to know what is the probability that at least 1 is a face card, and we'll take our answer as a percent rounded to 1 decimal place. So the only difference here is that we're drawing with replacement. How does that change everything? What's different about it? Because we're drawing with replacement, this does not involve counting things using either the permutation or combination formulas. Those are what we use when we have distinct objects and we're looking at how many arrangements or how many ways we can choose from those. When we're drawing with replacement, it just doesn't fit that. So we have to go back to the counting principle for problems like this. And that's the difference between this problem and the one you just solved. But still, with the complement rule applies, and we can calculate the probability that there's at least 1 face card by calculating 1 minus the probability that there aren't any face cards or that there are 0 face cards. So this part doesn't change at all. And that calculation of getting 0 face cards is really the key to the whole thing, because once we get that, the final answer will be just 1 minus that answer. Remember also that there are 12 face cards, so if we're trying to not draw a face card, we're looking for one of the non-face cards, and there are 40 of them because 52 minus 12 is 40. And as before, the number of ways you can get no face cards is simply the number of ways that you don't get a face card when you're drawing those 3 cards over any possible way you could draw 3 cards from the deck. And again, this time with replacement. So the answer for the 0 face cards probability will be a fraction, and we have to calculate the numerator and denominator, and we're home free. But as I said, we're doing it with replacement. We can't calculate with our combination formulas. We have to go back to the counting principle. And here it says we're just doing 3 events, 3 subtasks, however you want to think of it. And we've got to count the number of ways you can do each one. Well, if you're trying to not draw a face card, on the first draw, there are 40 ways of not getting a face card. And since you're putting the card back in the deck, there are 40 ways to not choose a face card on the second draw. And again, because you're putting the card back, there are 40 ways not to choose a face card the third time. So the numerator will be 40 times 40 times 40. How about the denominator? Well, same thought process, but in the denominator, you don't care what it comes out to be. It could be any of the 52 cards. And again, because you're putting it back in, you still have 52 cards to choose from. You don't care what the card is. And the third draw is the same. You have all 52 cards to choose from, and you don't care what the card is. So the result will be 40 times 40 times 40 over 52 times 52 times 52. That's 64,000 over 140,608. Now the answer they want as decimals rounded to one place and as a percent. So we need to change that fraction to a decimal at some point. You might as well do it now. Always take quite a few more decimal places than you think you're going to need. It says to round it to one decimal place, but it also says to write as a percent. Writing it as a percent causes you to move the decimal place 2 places to the right. Then you want another decimal place of accuracy, that's 3. So definitely take, I would say, 5 or 6 decimal places for sure. So I wrote it as 0.455166. Now remember, the probability of at least one face card is 1 minus the probability of no face cards, and we just calculated the probability of no face cards, so 1 minus that value is 0.544834. Now we're done except for the fact they asked us to do it as a percent rounded to one decimal place. So changing it to a percent moves the decimal place 2 places to the right. And then you can see that that first decimal place is a 4, but the hundredths place is an 8, so that 4 rounds up to a 5. So as a percent rounded to one decimal place, it would be 54.5%. So if you draw 3 cards from a standard deck with replacement, the probability that at least one is a face card is over 50%, 54.5% approximately. Now in the next section, we'll learn another method of solving this type of problem that you might find a little easier, but for now, this will get you there. Now how about a problem like this? I'm trying to give you variations of problems that on the surface sound very similar, but may have a different technique of solving them because other techniques that you've been using don't apply. How about this? A pair of dice is rolled 3 times. What is the probability we get a sum of 6 at least once? And this time, they're not asking for a percent answer, but they do want the final decimal rounded to 3 decimal places. We worked a problem similar to this before, except that we didn't roll a pair of dice, we just rolled 1 die. But I do want to go back and remind you of all those similarities. Not only is it similar to that one, but it's also very similar to the one we just worked with cards. The difference there is that we're doing probabilities based on 2 dice here instead of drawing cards from a deck. And as I said, it's extremely similar to one we did somewhat earlier in this lecture where we were rolling just a single die, but otherwise very similar. So I put up in the corner a screen capture from that calculation, and you can see what we did, and we just did it a few minutes ago, so it should be fresh on your mind. The point being, neither of the problems involving die rolls, either this one with 2 dice or the other one involving 1 die, which are independent events, rolling a pair of dice once and rolling them again, those events are completely independent of each other. The probabilities don't change because of a previous roll. Nor the previous card problem where we drew with replacement. Because we were drawing with replacement, that made those draws independent. None of the problems involve counting things with either permutation or combination formulas. We can't use those when we're drawing with replacement or any case where they're independent events. So again, we've got to go back to the counting principle for this solution. But otherwise, It's very similar to the one die roll problem. If you look at that in the lower right corner, the only difference is instead of looking at probabilities involving getting 4s, which is what the other problem resolved, we're trying not to get a sum of 6. Now, anytime you say the sum of rolling 2 dice, you've got to remember that we've got to go back and look at the sample space for rolling 2 dice. There's 36 possibilities, and we've done this multiple times. But just to emphasize this, in the lower right-hand corner, we went from looking for the probability of getting any 4s when we're rolling a single die to what we really want now, which is the probability involving sums of 6. That takes us to the sample space in the upper right-hand corner, which is a 36-member or a 36-element sample space. Once we get this, all we have to do is figure out the value that goes in the numerator and denominator, and I think maybe it's easier to start with the denominator. So let's look at the denominator first. Using the counting principle, remember I said we'd have to go back to the counting principle for these problems where the events are independent. We're going to do 3 rolls of a pair of dice. On the first roll in the denominator, we don't care what the sum is. So it could be any of those 36 sums. So you got 36 possibilities for the first row, 36 possibilities for the second row, 36 possibilities for the third row, and 36 times 36 times 36 by the counting principle is 46,656. That's the denominator of our answer for the probability of getting no sums of 6. Let's move to the numerator. Now in the numerator, we don't want any sums of 6. We're looking for the probability of getting no sums of 6. Well, if you look up there, there are 31 of them. 5, 1 adds to 6, 4, 2 adds to 6, 3, 3 adds to 6, 2, 4 adds to 6, 1, 5 adds to 6. In other words, only that diagonal line of sums that I did not circle add to 6. We want the ones that don't add to 6. And if you count those circles, or just say 36 minus 5 that weren't circled, you'll see that there are 31 possibilities. And again, this is a counting principle problem, and we've got 3 rows. On the first row, any of those 31 that I circled are okay. None of those 31 give a sum of 6. Again, if you roll a second try, same thing, 31 possibilities. Third row, again, there are 31 possibilities. All you're screening for are sums that are not equal to 6. And by the counting principle, 31 times 31 times 31 is the total number. It comes out to be 29,791, and that answer goes in the numerator. So if you take your calculator, you get about 0.63852. Again, take plenty more decimals than you need because you want to make sure your rounding error doesn't cause you to miss the problem. Also remember, we're not looking for the answer, not the final answer, as being the probability that there are no sums of 6. We're actually looking for the probability that you get at least one sum of 6, but we know by the complement rule that the probability of at least one sum of 6 will be 1 minus the probability of no sums of 6. We just calculated the probability of no sums of 6 being the 0.63852. So if you plug that in and subtract 1 minus that, you get 0.36148. They ask us not to change it to a percent this time, but just to round it to 3 decimal places. That would be 0.361, rounded to 1 decimal place. So the probability of rolling a pair of dice 3 times and getting at least one sum of 6 is 0.361. In wrapping up this lecture, I do want to say one thing. When you're practicing and working through these problems and similar problems, try looking at the big picture. If you're isolating each problem as a separate thing and just concentrating on solving that problem as you move from problem to problem, you're probably not seeing the big picture, and when you come back to those kinds of problems on the test, you may have trouble solving them. Now, I'm going to mention a few things, but this is not an exhaustive list. But for one thing, I mean by that, just the stuff that we've been dealing with recently about whether you're drawing cards with replacement or without replacement. When you're rolling die, 1 die, 2 dice, you've got to be careful. If the things involve independent events like rolling dice or drawing cards with replacement, you're generally going back to the counting principle because the combination and permutation formulas are generally used to count arrangements or choosing objects from distinct objects. And that simply doesn't apply when you're drawing with replacement or rolling dice. That's the first thing. You need to notice when you're reading the problem, is it an independent event, rolling dice, drawing with replacement, or is it a dependent event? If it's a dependent event, when you're drawing cards from a deck and not putting them back, generally you'll be able to count using your combination formulas. So that's one big picture item. Another thing I'd mention in closing is that the usual strategy when you're computing the probability of at least one of something, you handle that by applying the complement rule. In other words, go ahead and calculate the probability of getting none of those things, and then the probability of at least one of them is 1 minus the probability of none of them. There are other things I could mention, but I just want to get you thinking about looking for the big picture as you work through these problems. It's going to make your test taking experience much better.